Okay, hello everybody and welcome to Handmade Hero, the show where we code a complete game live on stream. We are, I think, at this point, we're sort of ready to begin some lighting stuff in earnest because we kind of debugged all of the crazy things that we had to deal with getting GPU stuff to work. Now, there will still be a little bit more GPU debugging in our future because we've got to figure out how we're going to compute the lighting not on the CPU side of things. So we do have a little bit more unsavory work to go, certainly. But we at least got sort of our basic framework stuff for the lighting working. So now when we run lighting code, in theory, we can have... Wait, or not. Did I leave this not actually rendering any lighting? I thought we left it... what's going on? What's happening? Did I forget where we left this? I don't know what this is saying. My evaluation period has expired. I didn't even know I was in an evaluation period. Well, that's unfortunate. Anyway, let me continue what I was saying before we deal with Microsoft's disaster there. So I thought we had left this at normal lighting, but it looks like we didn't do that, and I'm not sure why. So I take it back. Let's go ahead and find out what's going on with that. Let me jump in here. Oh, I remember what... Never mind. I do remember I lied. We were trying to add lighting direction. That's what was happening. So we stopped. We had just done this D bit here. So let me quickly uncomment that so that you can see what I was about to try and say lighting-wise, and then we can go and do that. Get it actually working. So in here we've got this, this inner product between the light direction RGB and the world end. That's actually the part that we haven't done yet. So that was why, I guess we did leave it intentionally that way. So this was where we left the lighting, and we were about to put lighting direction in there. The point of lighting direction was we're now that we have something that you can sort of see is starting to resemble a lighting solution, although isn't quite there yet. You can kind of see that it's like, yeah, okay, I could believe this will someday compute some lighting. It sort of looks like it's actually working per pixel and kind of relevant to where the lights are and all that good stuff. But when you take a look at it, you can kind of see that the surfaces themselves don't know where the light is coming from, right? So if you see like around here, that should be a hard edge. This is two sides of a cube, right? So is this. But instead of being a hard edge, it's just sort of this gradient wash. And the reason for that is because it has no idea where the light's coming from. So it doesn't have the ability to attenuate lighting reflection or change lighting reflection in any way based on the facing direction of the surface versus the light source. Because while it does know the facing direction of the surface, it does not know the facing direction of the light source. So it can't do the standard reflection computations that you might want to do to improve the quality of your lighting and take into account surface direction, which is a pretty important lighting cue for people. Now, maybe you want lighting that looks like this, and that's fine. There's nothing wrong with that. But it's just not probably what you want because it's pretty far from the way lighting would actually work. So what we're going to do is we're going to go ahead in here and put in a contribution from the light direction. And that's what we ended with last time. That's why it was black, because here we have doing the dot product with the lighting direction and the surface normal of the surface. And the problem is just we have not yet sent down the lighting direction, right? So what we wanted to do is now be able to send down the lighting direction, which might sound easy, but it actually takes a little bit of work on our part. The reason it takes a little bit of work on our part is because when we compute our lighting solution, remember, we're computing an aggregate lighting solution for various places in a voxel, right? We're using these light sort of reflectors to compute an approximate lighting solution for the scene. and we're kind of eyeing getting that down to the GPU at some point. So we're kind of doing, we're certainly not doing anything like ray tracing per pixel or anything like that. We're doing sort of some loose ray tracing for some sort of sparse elements of the scene to try and create something we can use to approximate the lighting everywhere to sort of a low fidelity result. And in doing so, we don't actually know where the light is coming from because we're not tracking that information yet. So in here, where we pack these values together, you can see this where we pack down the color. We also want to be able to pack down the normal. And so in order to do that, we need to get it from somewhere. You can see us getting like stuff like the emission color out here. What we need to be able to do here is also get the D value out. And so what I'm going to do is say, I think we already put it in here actually. Here's a lighting element. And you can see that I put in sort of like this situation here. That's sort of what we want to get out of it. We're going to ignore incident light for the moment. We're just going to use average direction to light. And that's the thing that I need to fill out. So for right now, we're going to do that. And we're going to have to track that value. So as you can see, that hasn't actually helped us at all, right? We're still going to be black because we're not filling out average direction to light. But that is our goal for today, is we want to start filling that out. So here we are in lighting test. I don't know why this ambient inclusion crap is still in here because we don't use it anymore, and I don't think we're gonna. So I may just nuke it. It's just bad. It's just in our way. What I could do is just do this. That way it's not in our line of sight anymore. And here's our compute lighting function. You can see us doing some iterations here. We then do ray casting, so on and so forth. And so now we restructured this loop at the end of last week to not be so weird. It was kind of weird because we came at it at a weird angle, so it wasn't really written as a straightforward raycast. Now it is written as a straightforward raycast. You can see that there's some number of iterations that are going to be done and averaged together. There's a destination index, which is to say each lighting element we're going to step through in series and do a bunch of raycasts to gather lighting from it. Again, this is not intended to be a final style loop. It's just intended to do something that we can practice with to get our lighting solutions to some place we want, and then we'll worry about optimizing them later. So then here's our ray count. We're going to cast 8 rays at the moment, but that's an arbitrary value you can set to whatever you want. Just makes it more accurate and slower as you increase it. We then go ahead and go through, it's an n-squared algorithm. We go through that's why I say we're going to have to optimize it eventually, because n-squared is the slow thing. We're going to go through all of the sources, which are basically the other lighting elements in the scene. And we're going to cast rays to see whether or not we can hit them, Whatever the closest one is that we get, right? We then say that's the one that would contribute from this ray. And so here is the case where we did hit something, right? Because you might hit nothing. And we might want to have something that happens when you hit nothing as well. You might get incident light from, say, skylight at that point, or something like that, like an ambient light. Okay. So once we get in here, you can see us taking a look at what the light is. I don't think we really need this light distance thing, but it's fine to check anyway. If two things are right on top of each other for some reason, we just want to avoid doing anything stupid. So here where we've got all of our lighting stuff, what you can see us doing here is computing the lighting and accumulating the total light contribution. What we really want to do here is start to expand this tracking to... yeah, you can, in fact, you can kind of see here. You can kind of see here we have some weird remnants of stuff, and like we should just clean this up a little bit. So that dest visibility isn't really being used anymore, if I remember correctly. So you can kind of see this is a thing that gets computed in this ambient occlusion stuff. I just don't like this stuff. We're looking at an old paper, and we did some of the stuff in there. You know what? It's just bothering me, so it's just gonna go. I mean, we have a GitHub and we have the old source zips. If we ever need to grab it out again, we can. I don't like that, so I'm gonna just start simplifying this down because I just want to get rid of things that I don't want in there. Where is that? There it is. So in the lighting element, I'm going to say we don't have this anymore. This is not there anymore. That's going away. The static information is the stuff that comes in, so that's all fine. The reference color, the transparency, the radius, the position, and the normal, right? So now let's start to try and work with this other stuff, and let's try to make something reasonable. So we have this front emit color and the back emit color. The front emit color and back emit color are what kind of light we're shining out on us. And that is all well and good, but the problem is we've sort of got two sort of things, and I'm going to uncomment this as well because we do it at the same time. We sort of have two different things that are happening here, right? One thing that's happening here is when we want to collect the light that's coming into a surface, and then we want to reflect it out on other things as we do our iterations for array casting, right? So we kind of have this sort of dual problem. There's a couple of different ways we can look at this. One way is we can not convect that light around. Let me just draw a diagram, because this is complicated enough that I feel like I'm going to have trouble explaining it without a diagram. So we've got a couple of different things, but think about it this way. So let's say this is an emitter. So this is set to actually radiate light outwards. And let's say this is just a standard reflector, so it doesn't have any emission, but it does reflect light. And here's the person we're computing, okay? So what's going to happen here is we're going to start casting rays out from this thing. Now, one of the rays might hit the actual emitter. And when it hits the actual emitter, that's fine. We know exactly what's going to happen here, right? Whatever the emission is of this, it's going to send that light to this surface, and that lets us know some incident light. So if we wanted to store, if that was the only ray we were sending, if we wanted to store the incident light and the average direction that light was coming from, we know exactly what it is. It's however much light this is emitting and whatever the ray direction was, right? That's all there is. Now let's say there's a second emitter. This is emitter 2. And one of our rays also hits that. So we cast 2 rays and we hit both of them. Well, what we can do is just add the incident light together, right? So we can have incident light, from 1 plus the light from 2, right? So it'd be like emit 1 plus emit 2 for both of these, right? And then we average the 2 directions together to get an average incoming direction. And again, not a perfect lighting solution, but in terms of just figuring out what the average is, there we go. Now we could do a little bit better than this if we want to, because we can take a look at the magnitude of each of these. So if this was really bright and this was really dim, we could weight the normal towards the bright one, because that's going to give a more accurate reflection. Since the majority of the light is coming from emitter 1, if the normal was more bent towards emitter 1, we would end up with a better approximate lighting solution by saying that the average incoming light direction is actually that way, not halfway in between them, since not very much light is actually coming from emitter 2, right? Again, none of this is perfect. And again, this is also where people start getting into a lot of crazy stuff. If you want to try and do better approximations to it, this is where things like spherical harmonics come in. Basically, there are other ways. I've mentioned this on the stream before. I'll just mention it again. There are other ways of encoding light that get increasingly more complicated. Sometimes they're good, sometimes they're bad. They have drawbacks. Spherical harmonics in particular has drawbacks of there being very hard to transform and stuff. But if you become familiar with a particular representation, such as spherical harmonics, you can get pretty facile with it and figure out how to do things that will lead to good results that aren't too expensive to compute. So there are other ways of trying to encode more information than just what the direction is on average. You can try to encode information about how it varied as well, right? So if you want to try and get a more accurate lighting solution, you can try some of these things. So anyway, so that's pretty straightforward, and that's something that we should be able to that's something that we can mimic pretty easily, right? Not much. There's not much fanciness there. I think hopefully everyone sees how we could modify that loop to do that. But The other thing that we might want to do is do this in an iterative fashion that's more like radiosity than it is like ray tracing. And what I mean by that is, now let's take into account reflectors. This is pretty straightforward because it's just raycasting to emitters, so there isn't any ambiguity about what we might want to do. Once we introduce reflectors, which are things that don't emit, which is most surfaces, but that we do want to bounce light to us so we can have some indirect lighting, which we would like to have, because direct lighting is not particularly interesting. Once we want to have indirect lighting, we do have a problem about how we're going to compute that. So one way to compute that is you always do the ray casting again, right? So we do a ray cast out to here, we find this reflector, and then we say, okay, well, let's cast another ray and see if we hit an emitter, right? The reason that that's particularly problematic is because it leads to having to do a lot more ray casts than you would like. So what we would rather probably do is allow the emitters to spread out to the reflectors first instead, and then when we hit a reflector, we know to grab it back, right? So the problem here is that it's like we may want to do some amount of forward propagation and then do our gather, and so it's just like with anything else, it's just a question of how we want to do it, and I'm not sure exactly what the right mix is. One way to do it is to always just do raycasting the entire time. That probably will be prohibitively expensive for us. So the way I was thinking of doing it is more like where we spread things out. So what I think we might want to do here is create a simple final gather loop that literally just casts out rays from this surface that we're computing, and it just averages the results it sees, probably based on magnitude. So it averages the color and then averages the normal weighted by the magnitude of the color. That is probably what we should do. And then what we'll do is split, instead of having that pass also be the thing that propagates light. Instead, what we'll do is we'll make it so that the emitters, we do one phase where we let emitters spread out to reflectors, and then reflectors will propagate out again. So what we'll do is, where here we've got this iteration going on, we will now have that global rendering lighting iteration count. That will only be for spreading out emission, and then at the end we'll have the final gather, right? Excuse me for 1 second. I still can't, unlike normally when I just have spread of a running nose, I think I am coming down with a little bit of a cold. It doesn't actually bother me much, but it does make me stuffy. Okay. So that's what we want to do, and that's why I say we kind of have some other stuff here. So like incident light and average direction to light will be the things that we would actually encode, and then like front emit C and back emit C would be the things that we will want to, those will be the things that we'll just use for that propagation pass. Now, the structure of this is rapidly turning away from the original structure that we had, but that's okay. Like I said, we didn't know going into it how we were going to do lighting. Lighting is one of the worst problems in computer graphics. Everyone does it differently. It's always a giant hack. And the reason is because, hey, it's really, really hard. The real world happens to do a really, really good job of lighting by using massive brute force. It just sends billions and billions and billions and trillions and trillions and quadrillions of photons out all over the place, and it's really hard to match that. It's hard to match it with, like typically when we have something like that, like a situation like this, where I have like a rigid object. Yes, nature uses billions and billions of atoms to encode what's happening to this thing. Fortunately for us, they all stay in a very rigid lattice structure most of the time, and especially to our eye, just look like they're all moving as one giant piece, or two giant pieces in the case of appliers, which is why we can do such a good job approximating those things. Lighting, not quite so much. Lighting actually propagates all that information all the time using billions and billions and trillions of little pieces, And approximating that is just really hard for us. That's why everything's always a hack. So again, moving away a little bit from the scheme we had before, but that's quite okay because, like I said, this is an exploratory process if ever there was one, and we're just kind of flailing around to try and find something that works well with what we've got set up that isn't too expensive and will possibly be GPU accelerable in the future, so that we can kind of move everything down there in a couple weeks when we have something that we think looks okay, and then we can just sort of have an okay lighting solution that our game can run through. So, all right, what we want to do then is split into two phases, I think, and I'll just separate these into two functions so we can see them a little bit clearly here. So what I'm going to have here is I'm going to have like a light propagation function, and then I'm going to have a final gather. I'll stay away from the turn of art for now. I'll just say like I'll say gather final lighting. This is called a final gather because in the rendering literature, and maybe not so much the rendering literature, in rendering practice, I guess I would say, that phase at the end where you say, all right, I've done whatever lighting computation I'm going to do for figuring out the lighting of the scene, but now I actually want to go back to all of my surface points that I care about and compute the actual lighting for output. That thing is typically called a final gather. And you can see why, because it's like, okay, I pushed light all through my scene however I was gonna, and now I'm gonna like grab that lighting in for any given point, gather it up, and compute the lighting. So final gather typically is that phrase. I'll stay away from it because it's kind of a weird way of saying it. So what we want to do here is we kind of have a little bit of annoyance. We've got something that essentially is completely... we've got two passes that are very similar. They're both going to do that raycasting. And I don't really want to duplicate the code for it because as we change these... as we change how these lighting elements are computed or stored, I would have to change both functions a lot in identical ways, which seems annoying. So I also need one more function here that these will both call per element that they're computing. And that will probably be the raycast, right? So this part here, that we've got this ray index part here, something like this is going to be sort of pulled out, right? So we're going to have a thing here that's like our raycaster. And so what I want to do here is I want to have a way where I can just say like, all right, we've got some number of rays we're going to cast. At the moment, again, that was set to 8, and that's fine for now, but that's something, a value that we'll actually think about a little bit later. And what we need to do here is probably abstract out this ray direction bit. In fact, we may want to just call this raycast multiple times. It's a little bit hard to say, but yeah, I think we probably want to call it multiple times. So maybe we want to stop it more like here, right? So we're going to come through here, go through all of our source indices. We're going to see whether or not we should skip it. So we'll probably still want that skip index in here. Because if you're casting from a particular element, you don't want to test against that element because they're coincident and you may record a 0 on an interaction that's right there. And so you just want to make sure you skip that. So then if we loop through each of the lighting elements in series and we get what we think is the source normal, and we check to make sure it's actually pointing back towards us, I guess, is what we want to do there. Yeah, so that's just avoiding the case where we wouldn't intersect and also making it so that we're not casting against the behind of things. That's not really correct in this case. So what I would point out there is since we want to use front and back emitters, because we have a lot of things in the scenes, we have a lot of like cards in the scene. So although it's more expensive, I think what we want to do here is actually have a like, I think we actually want to have something that's like front or back, right? So we'd set it to like 1 if it's front and 0 if it's back. So I think what we want to do here is say something more like we will, you know, we'll return a Boolean that says whether or not we hit. We'll encode a result that says, you know, here's whether or not it was the front or the back of the thing, and here's what the source was, right? The other thing we could do is just put the source information in here. So the other, you know, the other thing we could say is like, well, here's the like, we could copy the information out, right? Maybe let's do that. So maybe what we'll do there is say, all right, we've got sort of the thing that comes back. In fact, we could, we could do that. So what we could do is anytime we're going to raycast, we could basically just say, look, let's just return whatever the the contributing color and direction. You know the direction, that's the ray direction. So maybe we just say what the contributing color is, because we're only convecting light around here. So what we could do is say, look, there's a V3 that comes back, that's the color, that's all we're going to do, right? And that seems reasonable enough, because we can actually, we can handle everything else from there, I think. And it should be okay, I think. Yeah. All right, so if we loop over the sources, we do our tests, we see whether or not we hit something. So in this case, what we want to do is say, did we hit the front or the back, right? So what we're looking here is we're looking to see whether or not we hit the front or the back, like so. It would look like that, right? So we need to know whether we hit the front or the back or nothing. And the way we're doing this is saying, well, if the normal is pointing back at the ray, right? So if the normal is pointing back at the ray, here's the ray, here's the normal. If the normal is dots negatively with the ray, we know that this is a surface that's aiming at us, right? But if the opposite were true, if it were pointing this way, right, then we know we're hitting the back of the surface. So we have both cases, and we need to handle, or want to handle, both cases, right? Excuse me. So what we need to do here is say, all right, if we hit the back of something or we hit the front of something, we need to know which one we did, and we need to propagate those properly. And again, we don't have to use back emission. We could try just using front. And I'm just not sure. Let's think about this as well. So what we could do is we could say that when you have a surface that's got two sides to it, we actually put two emitters in there. And the reason that I'm thinking about this and I'm sort of stopping myself and going, hey, maybe I want to do that, is because we do have things like the cubes where the back faces shouldn't be considered, right? We only want to consider the outward ones. So I'm starting to think to myself, maybe what we want to do here is say that we only have one direction, the band, one direction. Like I actually want the band one direction to be in the game on every surface. We'll just texture map like their latest album cover. I don't know what that would look like. So we'll just take this right here, this picture, and we'll texture map that on all of the surfaces, right, in the game, and that'll be perfect. That'll be great. All right, so we want to say that there's just one direction per lighting element, right? And we'll put two elements together if we, just sort of slightly separated if we want to start simulating things that are two-sided, like the cards, as if they actually are two-sided, right? Which we may very well want to do. Like I said, that may become necessary to get some of the lighting effects that we want in the game. So, but I just don't want to complexify it by saying everything's got two sides, because if I do that, then I have to pay for both sides of lighting, even for all the cubes, which there are a lot of, that don't actually have two sides, right? And so we don't want to do that for everything. So I'm going to say, let's keep it like this, and that there's only one emitsi. So what I'll do is I'll loop over the sources, gather them out. When I do the raycast, if I happen to be facing this side of it, so it could potentially be a hit I care about, do the actual intersection. We want to only compute this if it's the closest hit that we got along this ray. So this part should still be in here. Don't we have an R32 max? We never changed the name of this, did we? Oh, it's, you know what? That is the new name. Never mind. I'm thinking old school. All right, so we got an F32 max. We pick the closest hit. And when we find a closest hit, we just need to store the color, right? So all we need to do here is say, well, whatever the source was, let's store that color, right? So I'll do results equals source emit color. We don't need to record which one we hit anymore, at least not for the moment, and off we go. So that raycast will tell us what the color is that we're getting back, and that's all fine. I don't know if we need this accumcy anymore. We may not, depending on how it looks down below, but I'm pretty sure we can actually simplify that as well. All right. So this raycast will take the closest thing and will give us whatever the emission was that was coming back along that ray, and that's exactly what we wanted. So then we come down here to compute light propagation, and we know we can use this raycast to do it. Now, I'm going to skip it for now, and instead I'm going to go right to gather final lighting. The reason I'm going to do that is because gather final lighting is actually the thing that we want to, is the one that's close to what we were already doing. So I can basically just take the code we had before and sort of use the raycast function to just do exactly what we were doing. So this whole thing here can just come through and be done, right? The other loop is going to be a little bit different. Well, it's not going to be that different, but it's fine. All right, so here is our gather final lighting code. I still would like to do a ray count. Here, this ray count may go up because for gathering the final lighting, we may want to cast more rays for gathering final lighting because it will not have any iterations, right? So it may be that, like, compute light propagation looks like this and casts 8 rays per propagation. It may be that we do like double the ones here and there's no iteration at all because we only want to go through the lighting elements once to do our final gather, right? So we'll come through here like so. This part, again, would only be in here potentially, but I don't even know if it's going to quite look like that. So when we gather the final lighting, we're going to go through each of the destination things here. What are we using the 2 camera for? Oh, that's the look direction for the actual thing. Yeah, so that's fine. That's when we actually compute how the lighting's going to bounce back. So yeah, and we don't even want that because then that'll get double counted. So we don't even need, I'm pretty sure this is not necessary because we're only going to compute what the lighting incident on the surface is. We're not going to compute the reflection. So this 2 camera part where we would be doing where we're looking at it from, that's going to happen per pixel later. So we don't even want this anymore, right? That goes away. All right. So we go through our ray indices here. We compute the ray direction by getting a random number, which we want. This closest hit stuff, source element, nonsense, blah, blah, blah. that all kind of goes away because now that's in a function, right? We've got to compute, oh, whoops. We've got our raycast function here. Now, what we can do is say, we could have an actual Boolean that comes back because we actually know whether or not we hit anything or didn't hit anything. But I'm just going to assume that we always hit something. And the reason that I'm going to assume that we always hit something is because we always do. In the real world, we always will hit something. And in theory, there should have been light on it. The chances that the light will be 0 somewhere should be, like, non-existent. So we're always going to assume that we hit something, even if it's a skybox or a very dim thing corner of the world. Most of the time we hit something, so I'm not going to try to optimize the case where we don't, because that's a case we actually don't want. We don't want the game to be pitch black anywhere unless it's like a level with no light in it, where you shouldn't even really be there because you don't have a light source yet or something like that. That's not something we need to optimize for, because most of our scenes will have light everywhere, so we need it to run fine when there's light everywhere. So optimizing for that case is meaningless, right? So what I want to do is I want to call our raycast, and I realized I didn't actually pass anything to the raycast yet, so lighting solution, what we're going to skip, and then the ray direction and the ray origin I will need as well. What did we call that in here? Relative source P is source P and dest P. So, okay, so we just have to replace dest P, right? We're using dest P there. That's going to be ray, origin. So there's our ray origin and ray direction. It's going to do a light cast from there. And that should be all the information, I think, that we need, right? I don't think there's anything else. So that's the function we're going to call. Here's compute light propagation, which we're skipping for now. And so then what I'll do here is call our raycast. I pass the lighting solution to it. We know we're going to skip destination index because that's where we're casting from, and we don't want to do that. 1. So we have our ray direction and our source location. Here's the raycast. Here's the incident color that's coming in. And what I'd like to do now is go ahead and do some computations with that result that we get back. And I'm going to ignore this accumulator for now. So as we gather the lighting, we're going through, we're going to get a bunch of incident colors back, one for every ray that we cast. We now know 2 things about it. We know the color that was coming back from that ray, and we know the ray direction itself that we used to gather it, right? So now what we want to do, we don't need this. In fact, I don't even know why we were calculating it to begin with. Again, this is just sort of the fact that this was kind of old code. We sort of massaged it a bunch of times in order to kind of get, like, in order to sort of put it into the final form. We're constantly trying things and experimenting things, so stuff gets in there that doesn't really make any sense. We don't need to compute this because we know what this is. This is the ray direction, right? We know that this was the ray direction that we were gathering light from. So that's really not important to have there, right? Okay. So when we're gathering this up, we don't really need to know any of this stuff. It's just not important. This is what we actually have. So now we've got sort of our light color. This is the incident color that's coming on the surface. This is multiplying by the reflector. We don't want that, right? So that multiplication by the reflection is something that's going to have to, that wants to happen out here instead, right? That's something that's going to happen on light propagation, not something that's going to happen when we're gathering. Now, why is that? Again, that is because what we're trying to compute here is the incident light on the surface, because we're trying to collect information about incoming light so that per pixel in the pixel shader later, we can compute what the actual reflected light is from a particular surface element. And in order to compute the reflected light from that surface element, we need to not have taken into account any reflection here, because it will be wrong, right? So what we're trying to do is just gather the light that comes in and save just what came in, and then later we'll do the reflection computation. Right? Okay. So we've got a distance fall off here. And these are always the kind of things that are a little confusing, and since I'm not a ray tracing guy, it's something I always have to kind of scratch my head about. In general, light along a ray doesn't diminish, right? So I don't actually know if this fall off really should be here. The inverse square law says that it should, right? But the fact that we're casting rays as samples into the world would automatically do that. So it's kind of, right, it's kind of difficult to wrap your head around sometimes for this sort of thing, where the different lighting aspects come from. But if you think about what I'm saying, so let's say I want to know how much the light from this emitter contributes to this surface, right? Well, we know that the inverse square law says that as the light comes in this direction, it gets dimmer proportional to the square for a diffuse emitter, right? For a diffuse reflector, right? And the reason for that is because as, however many photons are coming out of here, they get sparser and sparser the further out they go, right? If I'm emitting photons from this thing, then these two right here, might have hit a surface that was this far away, that was this big. But if I move it this far away, all of a sudden this photon hits and this photon doesn't, right? So as you get further from the light source, the number of photons that are going to be, the density of photons in any given area diminish because they're getting further apart, they're separating, right? But we are casting rays out from the surface that do exactly that, right? The rays themselves are separating and are less likely to hit anything out there that we encounter. So I'm going to say in my non-render guy way, that may very well be wrong, that we don't want to include a distance modulation here because the raycast itself already has that inverse square gather built in. And if we were to, on top of the sampling itself, including the fact that it will be less likely to hit surfaces based on direction, if I were to go ahead and put that lighting distance calculation in there, I might be double counting, right? So it's a really tough thing to call. It may be that this is not enough rays to really incorporate that effect sufficiently. I don't know. So, this is the kind of thing that I would go study if I were doing this for reals, like if I really wanted to get to the bottom of it. It's also something that we could ask a hardcore rendering guy about. They would know the answer to this problem pretty cold, because it's basically a question of whether your sampling already takes into account an effect of the lighting, or whether you need to take into account it into account yourself, right? So for now, I'm going to leave it out. It may be that it should have been kept in. As this number gets high enough, I'm pretty sure it needs to be taken out, because as that number gets high enough, the sampling definitely includes this information, right? I mean, at the limit, if you imagine casting billions of rays out from the surface, the inverse square law would then naturally be applied, because the averaging that occurs over all of those incident lights will naturally produce an inverse square gather from the surface. So my only question is, when this gets down too low, is that now the wrong way to think about it? I don't think it is. I think it still is. It just means your lighting solution's kind of inaccurate. But that's just true. I mean, oh well. So I don't think adding in a term that would diminish it is going to fix it, right? I think you just need to cast enough rays here to make it work. All right. So as we go, we have our reflection normal. Again, that's not important. We don't need any of this stuff. The speculative power, distance fall off, none of that stuff is getting included in here. at all. Although, you know what, I should probably save a lot of this stuff, because for the gather stage, this stuff is possibly important. So I'm going to move that stuff out here. All of this stuff like diffuse inner, diffuse contrib, and so on. Some of this stuff we'll use, some of it we won't. Let me just go ahead and cut and paste it all up here so that we can look at it again for final gather. Some of it's going to go there, but most of it is not, is going to stay in the propagation routine and won't happen in the final gather. So we'll get back an incident color. That's what's coming in. We still probably want to do the cosine. So I think we even don't want to do that. I think we just want to do a straight up. We just want to straight up sum these guys based on their intensity. I think that's all we really want. Because stuff like this diffuse inner product, to figure out how much contribution the light has to the surface, I think we actually want to save that again for the pixel shader, because that's where we would use that information based on the surface properties of the thing we're lighting. So I think none of this stuff wants to happen. I think that's all stuff that has to happen up here in the light propagation, and not, I think none of that wants to happen in here. So I think everything is just going to be, we get back an incident color, we do none of this. All we're going to do is say, okay, when we get back the incident color, we first want to find out how much incident color there is. So we want to do like a weighting, and so we want to get back a weighting, and that's going to be based on how strong the light is that comes in. We then want to accumulate this value. So we've got two values that we're accumulating. We've got the incident light and the weight. And really, if we want to, we can do these in place, but I'm not going to. So we've got an incident, we've got the incident light accumulation, and we've got the weight accumulation. So we can divide them out. Well, you know what? Even that, I guess we don't really have to. Well, yeah. All right. So I'm going to take the incident light that comes in. I'm going to multiply it by the weight that we compute, right? Oh, sorry. No, I'm not. That's what. Okay. Yeah. Got a little confused there. It's the incident direction. That's the one I wanted. So I'm going to take the incident color and just sum them, because all of the stuff coming in will count for now. And I'm not sure how correct that is. But I think it's roughly correct. It's hard to say. So anyway, yeah. I'm going to take the incident color. I'm going to accumulate that. I'm going to take the incident direction, and I'm going to accumulate that. But I'm going to accumulate that based on the weight, so that the stronger the light is, the more it contributes to the normal. And I guess now I think about it, I don't even need to accumulate the weight, because I'm just going to normalize that direction at the end. So I think this is correct, right? I think that's really all we're doing. We're getting back an incident color and we're accumulating it. We're getting back a sort of weight that we use from that, that we're going to use to sum the directions. And then when we're done, we just store these back. So then we take the destination. I was correct in that this is not necessary. So then we have an incident light here. And an incident direction. Oops. Caps lock. And that's just the normalized version, right? Because we know the length, since we know this normal has to be a normal, it has to be length 1. Normally what we do when we sum up things that are weighted is we record how much weight we had so that we can normalize at the end, right? But In this case, we don't really have to do that. And the reason we don't have to do that is because we know the normal just has to be a length 1. So at the end, whatever direction it's pointing, we just make it be length 1 in that direction, and we're done. So yeah, the weight doesn't have to be tracked like we normally would. So this is a pretty concise, easy to understand loop now. I don't know how great it is, but you know, it is what it is. We're basically just casting out as many rays as we decide we want to do our final gather. We sum up all of the incident colors, so that's the total amount of light hitting the surface is stored in the surface. And then we just average the normal in a weighted average based on how intense the light is. And we don't know what this value should really be. Right now, it's the what's called the 2 norm, right? It's the length of the vector of color, which is a reasonable approximation. But it might not be the one we want. We may want to use squared, like length squared. We may want to use the sum of the lighting values. There's a lot of ways we could do that, right? And I don't know what the best way to do that would be, but there you go. So, there's our gather. I'm pretty sure that all we really want to do here is say, okay, when we do gather final lighting, it's like this is probably going to want to do this in both cases. We're going to do gather final lighting on the solution, and that should just work. So now we just have to focus on the propagation phase, compute light propagation. And taking a look at this function, mostly what we're going to have to do is readapt it and sort of clean it out, but it's mostly, this is the function that's going to have to do the actual light computation to figure out how things bounce around the scene, right? So this one's going to have more lighting actually in it. So compute, oh, and this no longer happens. Oops. So we extract our reflectors, we compute the propagation between those reflectors, and then we gather the final lighting, and that is what we will send down to the graphics card for use per pixel. All right, so for computing light propagation, again, same basic idea, but this time what we're sort of trying to do is do some series of iterations that bounces light around the scene, right? And this we could do in a number of different ways, but I think what we want to do is kind of switch around how we're looking at it. Because I think we can optimize it quite a bit by doing it from emitters forward instead of doing it from reflectors backwards, right? And here's why. So let's suppose I do it, because there's two ways we can do this, right? One way I can do it is I can loop through all of the reflectors and do raycast outwards to find emitters, right? The other way I can do it is loop through all the emitters and project outwards to generate new emitters with every one I hit. The reason I like going through the emitters better is because there's only very few emitters when we start. Each scene may have like 5,000 reflectors and only like 10 emitters or something, right? 20 emitters, who knows how many. But there's a lot less surfaces emitting light than reflecting light. So on the first pass, we can just skip anybody who has no emission value, right? So I think that's what we want to do there. And I guess now that I think we do need that accum I was premature, so we are still going to need that because we don't account for it in one pass, right? Although I guess we could. So here's an interesting thing. So we could, if we wanted to, allow people to propagate within the same frame. I shouldn't say frame. Within the same iteration, we could allow people we write to later to actually continue propagating that light onwards. I'm not going to do that, and the reason that I'm not going to do that is I'm going to say that we want to prepare this sort of to think about it working in a very parallelized way. And so what I don't want to do is ever write to any value I'm reading, right? I want to have like a strict input-output buffer kind of a thing. So I want to be reading from the emission color and outputting to the accumulation color, and then swapping the two, basically, is what I want to have happen, right? So maybe like, you know, we could even call this like send color and receive color or something like this, or, you know, this is the color that's emitting now, and this is the next emission color or whatever. So it just kind of gathers them up as it goes. And so, yeah, I mean, I don't know, right? Like, but that's the idea. So as we come through here, we're going to do compute light propagation. I'm going to say like, okay, you know, let's loop through each of these saucy gentlemen here. And what we're going to do is say, much like we did before, we're going to raycast this. So for each of these destinations, we're going to do a bunch of raycasts here. I don't know how many we're going to do, but a couple, right? Previously we were doing 8, so maybe that's how many we're still doing. Or maybe we may reduce that because we want to have more iterations and less rays, or who knows what, but something like that's going to happen, right? So we're going to go through and we're going to say, instead of dest index here, I'm going to change this to emitter index, because that's, I said I kind of want to loop over the emitters. Here's the emitter. And what I want to do is say, you know, if the emitter's emit color is greater than 0, then it's something that we will actually raycast from, otherwise not. And the other thing we can do here is this could be a, you know, another value. So if we wanted to, we could say, look, if you don't have at least, you know, a little bit of light coming out of you, we're gonna assume you can't really contribute to a propagation phase. So that value is tunable, right? You know, down the line. So when we come through these emitters, we're going to say if this is somebody who needed to emit, we will raycast at that point, and we'll say that you know, we want to skip the emitter itself because obviously we don't want to hit that. But we want to raycast and we want to see who we hit. Now we do have a problem here, which is that we didn't actually. We want to write to that person who we're targeting, and our raycast again, like, because it's nice and simple for the final gather. Unfortunately, we don't have the ability here to know who we actually hit, right? So we would need to expand this to include that. As much as I didn't want to have to do that, we do need that, right? So we'll send the index and the color back. So we'll set the color to 0. We'll set the index to element count, and then off we go. So in here, that's all we really needed, right? Is just to remember that. Then when it comes back, both of these guys get what they want. So here, when we have this raycast, we don't care what the index is, so we just use the color. In here, we care about the index, so we just use the index, and off we go. So here in this raycast, we want to take a look at what the index is. So here's our hit index, like so. If the hit index is less than the element count. This value right here. We know it's valid. And so what we want to do here is just take this and add the light that we are trying to send. Basically, we're the emitter. We've found somebody we should transfer light to, so let's transfer that light. Right? And that's all we're doing. So I believe to think about this now. I believe this is the place where we should, in theory, be able to take into account the inverse square law more directly. So we're just looking at the transference of surfaces here, surface to surface. So I believe this one would work. The only thing I'm not sure about is we can hit the same surface twice, and we don't really want that. So the kind of convoluted way we had it before, we actually looked at each individual surface to see whether it could see it. So in this case, what we want to do is sort of prohibit ourselves from writing to the same person twice if we happen to hit them more than once. And I don't really know the best way to do that, right? Which suggests that maybe the emission process also wants to just be kind of stochastic and not take into account things like light distance fall off and so on, honestly. Yeah, so I'm not really sure about that one. That's a little bit tricky. Because essentially there's two ways we can look at this. One way is we can look at this as a complete n squared problem where we want to consider every emitter and every receiver and see whether or not we can see each one from each other and do one light transfer per round. The problem with that is assuming that our raycast, we start optimizing the raycast part, because that's the expensive part of both of these, we really don't want to be n squared anymore. We want to just be able to do a quick raycast that uses some kind of acceleration and then determines who we hit. So it almost makes me feel like we really just want to do this. Maybe we really don't want to do the emitter-based thing at all. Maybe we just want to do stochastic samples always. And we just run them repeatedly. I don't have a strong opinion one way or the other. But just thinking about this, it really does kind of seem to me like we want to, you know, we want to have some, I think we really do want to stay stochastic and accelerate the ray count. You know, just try to be able to increase the ray count and so on. So yeah, I'm just going to say that that's what we want. So there'll be a weight and a color here. So as we go over these, when we find an element we hit, like we'll take the next emit color, and we'll basically compute whatever the lighting transfer is going to be from the hit, and then we'll weight it up, and at the end we'll normalize those weights into the final value. I think that's what we want to do. All right, so now we actually have to figure some of this stuff out, how much the emission, how much emitted light there's going to be, and that sort of stuff, right? So we're turning this surface into sort of a virtual emitter, if that makes sense. And again, this isn't accurate because we're not doing full scene ray tracing. So per pixel, we just have to have an idea of how things are sort of bouncing around the scene. So everything's kind of a chalky reflector. For purposes of this propagation pass, there's not going to be a lot of like focused light reflection and caustics or any of that stuff we're not going to capture, right? So specular surfaces at render time we can do, but at bounce time we're not going to be supporting really. Okay? So now what we need to do is figure out, all right, how much light is going to come in here. And so what we know is we have our emitter, and we know what its emission color was, right? So we're starting with that. Now, we do want the incoming direction to vary by the cosine, because we're storing up the amount of light that hits the surface that we're going to then send back. So we do have an inner product in here, right? So we do want to take the inner product of the ray direction, so the direction we're casting out, which again we're going to have to which we're going to have to compute here. So from the emitter, for each ray, we have to take the emission normal, and we're going to take the ray direction here. That's going to come out from the emitter, right? We could call this more specifically the emission direction. And of course, we know it's coming from the emitter origin. There we go. So we do that ray cast out. When we compute the light color, we take the inner product of that emission direction, and we need to clamp it with the surface normal that we hit, right? Now, we want this to be 1 when the emitter direction was directly, when the emitter could be seen directly above the normal exactly. And remember, the emission direction is coming out of the emitter. So we actually need to negate these, right? Because they're facing opposite each other right now. The emission direction and the receiving normal are facing opposite each other. We would get a -1 in that case, and we want the opposite to be true. We want 1 in that case. So we have to flip the sign of that around so that the cosine fall off works properly, right? So that's the amount that's going to come in here. But then we also want to take the Hadamard product. I'll pull this out here so that we can. Or I guess we'll call this angular attenuation. Right. So there's the angular attenuation. And then we also want to take the Hadamard product here with the reflection color, because whatever the thing is that I hit, it's going to reflect that light out by multiplying it here. Now, what you can see is that's wasted work, because this reflected color is going to multiply every attenuated incoming light. So what I can do is instead wait till the end. So after we've done everything, wait to the end to do this. Right? So if I sum up all of these, only using the angular attenuation, then at the end what I can do is I can loop over, and I guess, sorry, this needs to be inside the iteration, obviously, is when I run through everybody again at the end, I will look at all of the reflectors. And again, this is really just nomenclature of how I'm thinking of them. I'm thinking of emitters here, I'm thinking of reflectors here, but they're the same elements, right? When I come through here, what I want to do is I want to say, all right, the emit color is going to now have whatever that summation was, it's going to be multiplied by the reflected color to sort of take all of the incident light we summed up that was in this, that was going to bounce off the surface. It's going to get modulated by the reflected color because, you know, if this is only a red surface, we should knock out all the green and blue light there or whatever, right? But again, I just pulled out, that would have been a common term across the entire summation. And then I also want to average over the number of samples that got hit here. So I want to say, okay, in addition to that, I need to take whatever that lighting count was there, and I need to do 1 over the lighting count, right? So I need to also multiply it by that next emit C. Needs to take the next emit W and multiply it over it. So, right, so 1 over hit next emit W. Like so. Now we don't need to do that in the case where there is no hits were recorded, right? So we can do that comparison and continue, so that's fine. And we may want to store this as an integer for that purpose in that case, because we're just sort of counting up. But that's not super important. That's like a fiddly detail at this point. So after we do all of these, we know how many hit each individual reflector. We're going to go ahead and correct for that weighting factor there, right? So each sample that came in, we're going to correct for that. And then we're also going to knock out using the reflection color. We then need to clear everything out, right? So this clears everything out so that we can then do a summation, another pass summation. And this stuff I think we don't really want anymore, right? We just don't need this. This is stuff for computing the final lighting. And it's just not something we need. So if we go back and look at the OpenGL code, right? Excuse me. And look at all of this stuff. This is stuff that we then eventually want to put in there, right? Like all of this stuff right here is sort of stuff we want to put into the fragment code. In the future. This summation is not necessary anymore because we're kind of doing it in here. So I think that's really all we need. That's pretty much it, right? And here, honestly, we could just do this per channel as well. We could just say if emit C, R, emit CG, emit CB, right? You know, something like this. Right? We don't really need a length squared. We just need to know if any of the channels summed up to it, right? So I think that's roughly what we want there. We now need to set sort of our initial stuff where we do our extraction, because we have to clear this stuff properly and make sure everything's set right. So when we do our extraction, you can see how we set these things here. We've got front emit C and back emit C and nonsense like that. So we kind of know we're not doing that anymore, right? We're not doing a back emit C. We're just doing a regular emit C. And I think, do we clear these normally? I don't know if we actually clear these. Yeah, we need to actually clear these in here. So we need to take these two values and set them properly, right? So we need to say like next emit C. Oh, I don't know why we set those both. Okay, there we go. Right, so it looks like we want it like that. So we have our emit C, our next emit C, and our next emit W. Like so we just get those set properly. I don't think we need incident light or average direction to light because those will get set directly and they don't need to be cleared to anything in particular. So the same thing has to be true in this function as well, because we have two different ways we can extract the vertices right now. Again, looks like this is not relevant. So we have an emission here. We have a next emit C of 0 and a next emit W of 0 as well, right? And those two are just, you know, sort of ad hoc extractions that we were doing. I don't know why we pulled elements out there. It doesn't look like we really need to, so maybe I'll just do this. Well, no, you know, I like it out there. Let's do it. Let's keep doing it. All right, so this has to actually return a raycast result now. I didn't actually change the return value, even though I re-implemented the function to have it. That was just a weird typo there. Don't know why I did that. And let's see here. So now we've got sort of these old output lighting quad stuff. So we don't really have this visibility value anymore, so I'm just going to get rid of that entirely. And these are just going to be our emit Cs. I think what we really want to draw now is that incident color, but we can leave this as emit Cs for now. We probably want to be able to draw both of them. But the emit Cs are the colors that we actually were sending out from those surfaces, which is the information that we probably want to draw. But we really want to see both. We want to be able to see both the emission color and the incident light summation, because both of them are relevant. So, all right. So now when we're packing things down, again, that color now wants to be the incident, or what is it, average direction to light. Oops, that's D. Sorry, average. This is incident light. So this wants to take the incident light, not the front emit. And that's going to pack that down. So now we're storing the incident light in C, and we're storing the average direction to the light in D, which is the information we wanted. This is just some debug code, but we'll keep it working for now, because why not? And then inside the shader now, so this is actually now more correctly stated. So this is the light color, and this is the light direction, right? And we're sort of taking a look at, all right, so what is this code doing? So that's a distance fall off. which seems okay because we're not sampling multiple rays, so we kind of have to do that. And then we've got a inner product between the light direction, which we want, and the world normal seems correct. So I think that's all correct. Now, we just did a ton of new code there. So we're going to have to do some debugging, which means probably, how much time do we have left in the stream? Probably I will leave it for next time because this ain't going to produce much. Wow. That was actually better than I was expecting. Doesn't look correct, but I was expecting just like complete garbage or something. Yeah, all right. Well, that was more than I had hoped for. It's kind of trippy. And kind of cool, actually. And pretty fast, oddly enough, as well. So yeah, that is a lot closer to done than I was expecting. We're getting there, folks. The long, slow struggle of lighting. But yeah, it's not great yet. I also don't know why we're not getting any yellow light transmission here. So something bad is happening there. Why there's no pickup from the yellow light on this, I don't know. I don't know if it's because there's too much shadowing happening or something. And also, like, the red-blue light transmission here is kind of out of control. So we've got a bunch of stuff to work on. But I'm pretty happy with that. What I would like to maybe do is take out some of the additional emitters here. So if I go into, for example, worlds mode, I don't remember how we were setting these emitters here, but like snake segment, for example, add piece light. So if I were to take out the add piece light for the snake, I think we're probably going to want just this one light source in here, right? So that way we can sort of see man, this is starting to be kind of cool. Like as you move around and the lighting changes on you, like it's kind of all busted right now, so it's not really good, but it's just fun when you get into those sorts of situations, right? Like when you can see the lighting sort of start to change and whatever. I don't know. Starting to have sort of almost a real render. Not quite, but almost. So yeah, like I wanted to take out those additional yellow lights because when we first start debugging this, we're going to want to look at just what happens with one light source so we can have a better feel for what's going on there, right? So that's what we'll start working on next time, and I'll try to get Visual Studio's registration stuff straightened out so we can debug. I'll go to some Q&As now as well. Please increase the font size in Visual Studio for debugging. The font size is pretty small. It's not the same as 4Code uses. Problem is, of course, I can't do that today because Visual Studio is doing its thing. I wonder if we should just make an account. Try to remind me next time, tomorrow. I could try to make a note of it too here, I suppose. I don't know if I spelled commensurate right. Shareware Visual Studio. Yeah, so I don't use the shareware version of Visual Studio. I bought the professional one that I use at work. I still use 2012. But I use the shareware version on the stream because that's what everyone else is going to have to. Like, I don't want people who are trying to learn to program to have to go buy the professional version of Visual Studio. Especially because it's not worth the price. Yeah, I do have an account. I got to go look up what the password is. I don't know what it is. So I'll go look it up and then I'll sign it in after the stream is done. And yeah, and the reason I didn't use ForCoder, I ran Notepad to type in the to-do is because I want it to be a window, like a separate window that I won't close, right? Because I'm going to close ForCoder in a second, and it's going to be, I want something that's stuck up there. Yeah, no malicious intent with their statement. I just find it funny how it expires after 30 days without you giving them customer data. Yeah, so there's a couple of different things about it, right, that I don't like about the Visual Studio thing. First of all, like, I'm happy to pay for software, I like paying for software, actually, and I miss it. And so when a piece of software package has two things going for it, I'm pretty happy. One, it does not have DRM. So I can just take the executable package and whatever, check it into source code control, pay my money, whatever the price is, and be good. That's thing one. And thing two is that the price of the software is roughly commensurate with what it does, and that it does the thing that I want, right? So Visual Studio kind of fails on both accounts to a large extent. I don't use Visual Studio because it's good or that they even are attempting to have me as a customer. I just use it because there is no really other debuggers right now, right? There's really almost no competition in that space. There's competition in like the reverse engineering space, like there's IDA Pro and stuff like that, but not really in the just regular source level debuggers for people who wrote their own program, not who are trying to inspect someone else's program. So like good examples of software packages that I love paying for: Reaper, the audio package, priced very reasonably for what it does. There's no DRM at all. You can just check it into your source code control. There's just a registration key. You just save the registration key and you're good to go. It's targeted at the people who it's targeted at. Like, it's like, hey, this is for recording professionals. Every change they make is for recording professionals. Like, it's great. It's a great software purchasing experience. Example of the worst possible software experience: anything from Autodesk, right? Massively more expensive than the value it gives you, because usually they're targeting like thousands of different use cases, only one of which is relevant to you, and you're paying for all the rest of them. Extremely intrusive DRM. Even it installs like rootkits on your machine, more or less, right? Cannot be checked into source code control, right? Cannot be efficiently distributed throughout your team. And Microsoft has sort of gone from being in the first camp. When you used to buy Visual Studio, you just got a CD. You could install it on a computer. There was no DRM. You could check it into source code control. It just worked. You paid your money. You had it. All the features were geared towards you, right? Professional developer, programming in C. Now they've gone 100% Autodesk. Tons of features for everyone and their grandmother. Most of them are relevant to you. Last time they cared about game developers was 1983. That's a joke. Obviously, it was more like 1995. The price is astronomical compared to what you're getting for it. It's DRM all over the place. Even the parts that aren't DRM'd, you can't even check into source code control because there are 8 million weird like side-by-side assemblies it installs and blah, blah, blah. So, nowadays I try to purchase as little as possible from Microsoft because they went, They basically went from selling software the way that I purchase software and the way it makes me effective to selling software the way that just makes my life miserable. Did you try Connie Moo instead of stock command prompt? I love Quake console effective delivers. I don't spend much time in the command console, so I don't complexify my install by using a custom one. If you're somebody who spends a lot of time in the console and writes lots of stuff there, then that may be a good idea. Final Space says the good times for paying software and are happy are totally over. Yes, there's like a few very specific software packages where you still pay your money and get good service in return. They're vanishingly small. Reaper is like one of the last remaining examples, right? Couldn't follow for a long time. Have you done something with automated unit testing? Or are you planning to? No, we don't really have much that needs unit testing in this package, in this program. So there probably won't be any automated unit testing. There might, if we want to get saucy, we might do the game industry version of unit testing, which is because generally, except for some core systems, unit testing doesn't really buy you anything in game development because it only finds your really easy bugs. The really hard bugs are the ones that come from things that evolve over time in the game. But there is sort of a game development equivalent of that, and that is sort of like randomized input testing or even structured input testing, where you basically write sort of a bot almost that tries to run your game in various ways and sees if it can break it, right? And this is great. It is sort of the equivalent of unit testing for like web stuff. Unit testing is good at finding like server bugs because servers have well-defined inputs and outputs that you can run unit tests against. Unit testing is crappy for finding game bugs because it can only find the easy game bugs, like bugs in your memory allocator or bugs in your asset loader. Like, okay, great. Like, yeah, maybe that's worth a little bit something, and if you have a summer intern, have them write them, great, go for it. But the problem is the really hard bugs in game development are the ones that come from odd interactions of the game over time, and unit testing does zero for this. So, but that doesn't mean that automated testing is a bad idea for games. It just means that you got to use it's not unit testing. It's actually sort of more constructed randomized input testing, and it works very well. So we may, if we get saucy at the end of the project, we may try to do that, because you do find a lot of bugs you would not have found if you do put stuff like that in there. All right. I'll just quickly answer this last question. How do you keep your motivation going in long-running projects? I don't really have a lot of troubles keeping motivated to work on stuff. What I do have, the two problems I tend to face are just getting too stressed out, because I'm fine. Like, I could spend 10 years working on a project, but nobody wants to pay for that, right? And so I get really stressed because I'm always behind, because I'm always like looking into things or experimenting with things when I probably should just do something stupid and move on. So that's more a problem I have. I don't really have the problem with the motivation. I'm like, usually my problem is the opposite. I'm too motivated to go solve some problem that really probably shouldn't be looked into at this point, right? That's why I'm kind of more of a research coder than a production coder. I'm like on the research side of production is where I tend to be more successful. And straight production, I'm actually much worse, because I want to go look for new ways to do things. I'm too motivated to do that. And what I almost need is a decrease in motivation. I almost need to, like, I would be better off if I just wanted to get things done quickly sometimes and just wasn't motivated to go do more work on something, right? So there's that. And the other problem that I tend to have is, what was I going to say? All right. I don't remember what it was. Sorry. What was the other problem? I don't know. Yeah, I don't know. But yeah, that's typically the problem. The main programming problem I have is wanting to go solve problems that don't need to be solved right now. And I don't really think of that as that much of a problem as a requirement, right? It's like that basically means that when I'm taking on stuff, I need to do stuff that benefits from research focus because otherwise I'm just going to take way too long to do something that doesn't need, I'm going to spend time improving something that nobody wanted improved, right? All right, I'm going to wrap it up. Close down everything. Thank you, everyone, for joining me for an episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along with the series, you can always go to handmadehero.org. And if you pre-order the game on handmadehero.org, it comes with a source code, so you can play around with everything yourself and do your own experimentation with the source space as it is. Maybe you can fix the lighting before tomorrow, and you can debug it before I do. We also have a forum site you can go to if you want to ask questions, a Patreon page if you want to support the video series, and mostly that Patreon actually goes, I disperse it out to people who are making stuff that support the stream, such as the fabulous annotations done by Miblo or the Handmade Network that runs the forums, among other things. So really that supports the whole community. We've got a schedule bot, which tells you when we're going to be live. If you want to subscribe to that, such as a Twitter bot that will tell you when we're going to be live so you can find out when episodes are going. And we also have an episode guide you can go to if you want to catch up on old episodes of the series. That's about it. I will be back here tomorrow when we'll start debugging the lighting and trying to get it to produce good lighting results. It's starting to look kind of useful, so that should be fun. I hope to see everyone back here for that. Until then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.